Yeah, we are a small company, and we do consulting for enterprises. And actually, we build neural networks and train them for various applications for various large enterprises. And for this particular talk, we picked NLP because it really pushes the limits of computation, both on the training side and on the inference side. And it's a very good, Minsky's work really well. IBM Power Systems work really well for this. So that's the topic we have picked. So classical NLP versus deep learning based NLP, just to point out the distinction and to motivate the reason why deep learning based NLP is so compute intensive. The classical NLP is typically handcrafted features. So you guys have probably heard of ontologies, and the various grammatical structures are kind of handcrafted into features, and that is used to extract meaning from text or speech. Also, these are keyword, string, or rule-based systems, and they rely on large set of grammar-based ontologies and heuristics. So what this means is that it is very difficult to go between languages, and for each language or for each particular idiom or for anything, you have to now start handcrafting these things all over again. Neural networks, as we know, they learn the features, so the features are auto-generated, which is very cool. You don't have to handcraft these features. Word and sentence embeddings, in other words, thought vectors, are learned in an unsupervised manner. So if you train your system on a particular corpus of text or documents, then it will pick up the features and will pick up embeddings and concepts and jargon and acronyms from that corpus. And finally, if you do search or extraction or queries of any kind, then because of these above features, you can actually extract meaning based on, you can extract information based on meaning, rather than just a pure keyword-based or string-based search. So this is just an introduction. The basic concept of word embeddings or thought embeddings is illustrated in this slide, and it is quite spectacular how well this works. So a thought vector is essentially a way of representing a certain sentence or a set of words as a string of numbers. And as a sequence of numbers is a vector in an n-dimensional space. And the magic that happens is illustrated. This picture over here illustrates how if you do your unsupervised learning and if you create your thought vectors and your sentence vectors in a proper way, then the embedding in the latent space actually contains meanings, contains grammar, and all of that stuff is embedded in there. And this is the reason why deep learning based NLP, you do not have to do kind of handcrafted features, or you do not have to rely on rules of grammar or ontologies or such. And yeah, the illustration is that you can see that if you look at this is a cartoon. This is just a two-dimensional representation. The actual thought vectors could be 512 dimensions or in a very high dimensional space. Typically, we work with 512 or 1,000 dimensional vectors. But this is a caricature. It illustrates the point very well that if you can do stuff like you can put semantic concepts into an equation, because you can map the word king to its thought vector representation. Each of the words, you can map it there, and then you can do very simple math like add and subtract. And look, the addition and the subtraction in this latent space, when you do that calculation on the left side, you come up with a number, you do a reverse lookup and you see what word that translates to, and it's quite fantastic that it would come up with that, right? So if you stare at that, you can see that for an English speaker, that seems to make some kind of sense. That you take man away from king, so you still retain the notion of royalty maybe, or a ruler of a kingdom. And then you add back woman into it, and hallelujah, that's queen. And that's the sort of stuff. So that's an illustration that these word embeddings, sentence embeddings are actually capturing some notion of grammar, some notion of semantics, some notion of meaning. Right. So just to go over the bullet points, applicable at word, sentence, and even document level. Although the longer and longer your concept becomes, the harder it is to extract robust embeddings. But word and phrase level embeddings are quite popular, quite robust, and is generally the de facto way now to work with NLP systems. You can do neural networks to kind of even bring it up to a document level using sliding convolutions or some other stuff like this. It performs best when trained with an application vertical specific vocabulary because after all, while these neural networks have a lot of potential to extract the meaning, but they work best if it's a limited domain. So we have seen applications with financial document sets or legal, etc. And for a particular domain, it really works very well because this kind of concept extraction, it really works well. Right. Now, of course, this is nowhere near human level comprehension. So this stuff is really good for tasks that are simple for humans. You know, I would say a 5 to 6, 7-year-old who is in their native language, that kind of complexity, you know, small vocabulary, simple concepts, don't expect this to do too much. But boring, repetitive, error-prone tasks, like just reading through a document and checking for some certain things, etc., can be very well and very well automated. Now, the thing is that you usually use a mixture of supervised and unsupervised learning. The unsupervised learning is used to create the word embeddings and the thought vectors. So you don't need labeled data set, right? You can throw entire Wikipedia, entire encyclopedias at this thing, and it just cranks away and tries to learn the structure of the language, tries to learn the grammar. Now, of course, like all things in deep learning and like the previous speaker was also showing, you know, these are computationally very heavy tasks. And typically to create these word embeddings and thought embeddings, they take multiple weeks on a single GPU, so you need to parallelize this and run it across and use some of the techniques that was described also previously. Once you have got your word embeddings and your thought embeddings for your particular application domain, then you can deploy some supervised learning to do specific tasks. We'll come to examples of that. Yeah, like I mentioned before, don't expect this to write a book or to explain to you, read a book and to explain to you what the book means. That's way beyond it. But simple, mundane, error-prone tasks can be very effectively automated. Examples are database normalization, data set merging, document comparison and retrieval, document summarization, data entry, etc. So, for example, you could do a semantic search and say, find in my corpus of documents inside an enterprise, find me all the documents that are similar in meaning. So you do not rely on keyword search. You do not rely on your search query having the same terms as you would have in the document, right? So you could have a search query with no words in similar to what you're searching for, because you could have synonyms, you could use different jargon, you could use different acronyms. So you truly extract. So the basic idea is very simple. You extract meaning from the question. You go through all your documents and you extract the meaning, and then you do a comparison at the semantic level, at the meaning level, rather than doing a string compare or a string search. That's the basic idea of kind of an NLP-based search, right? First, you turn your question into an embedding, and you turn your documents into embeddings. And then, of course, you cannot do a simple kind of a Euclidean distance or a simple comparison. So you have to have a different notion of equality and use a neural network to implement that. So the basic framework would be turn your sentence question into an embedding, turn your documents into a set of embeddings, then use a neural network to compare those, and that neural network essentially defines a different notion of distance, right, rather than some simple Euclidean distance. And on this basic framework, you can tackle many problems like this, use cases like this, and you can see that in modern enterprises, banks, or legal firms, or even going through manuals and stuff like this, wherever you have large corpus of private and secure documents, these techniques really help to index, to search, to categorize, to summarize, etc., basically anything that is text. Right. So let's come to the focus of this conference. Like I mentioned before, training is essentially the process of creating custom thought and word vectors. As should be quite obvious, compute workload scales with training data set size. Now, when you're generating your word embeddings, when you're doing your unsupervised learning, the larger the data sets you use, the better it is, clearly. And for sensitive data, enterprises prefer on-prem versus Azure. So typically, they would set up clusters on-prem or have like some co-located data center for this. On the inference side, compute scales with the number of users and the number of documents, because you have to kind of go through them and do the comparison across each document, as I described before. So you can see that is a huge compute load, right? If you're getting a dozen queries in a typical enterprise, dozen or a couple of dozen queries per second are coming in, then you multiply it by the number of users, by the number of simultaneous queries, and by the corpus of your document, what size that is. So this is very unique, because in a typical neural network application, the training is orders of magnitude higher compute requirements than a single inference. But in this case, because of the nature of this problem, your inference could also be very compute intensive. And if you have a lot of users or a very large corpus of documents to search through, then your training could start equaling the supervised part of the training. The unsupervised part is done once, and you can keep reusing the word embeddings. Inference compute, I guess I just talked about this slide. Yeah, so machine learning, NLP, it is, we have all implemented kind of, or any one of us who are programmers here, we have all implemented, string search and stuff like this. And, it is a few 10, 20 flops, per word of string compare. On the other hand, the deep learning NLP-based search is of the order of 10 power 5 flops, right? So yes, this deep learning is doing some very cool stuff and is able to extract a lot of meaning and stuff like this, but it comes at a cost, and that's the cost. Response time, of course, for search and stuff like this is critical to user satisfaction. And hence, you have to have dedicated resources are spun up based on user activity. Deep learning jobs are compute limited. The reason that bullet is there because we have run into customers who are used to, old school kind of NLP, classical NLP techniques. And usually over there, because it is not compute limited, it is typically IO limited in the previous world. Then when we run into customers who are used to that, and then when we say, hey, this job requires a lot of compute, they would say, why don't you just spin up another thread? Because they are used to a world where the CPU is maybe at 5% or 10% loading because the thing is IO limited. Whereas deep learning is you just flip, it's just the other way around, right? This is severely compute limited job, especially this kind of NLP jobs that we are describing. And then you run into the problem where you have to explain to the customer, hey, I can't just spin up another thread on that CPU. I need to add more hardware. So it takes much longer because the compute requirements don't underestimate how much you need. And this is what we tell our customers. It's great news for IBM because they'll be buying lots and lots of IBM Minskys, hopefully, to run these kind of jobs. Right, so I apologize that this table is not yet filled in. We did the best that we could in limited time. But this is inference execution on about, I believe it is on about 10 to 20,000 document corpus. So not too large, but it's a typical small enterprise private corpus. And we have profiled it on different machines. It's not quite apples to apples, I'm afraid, over there on the left side, but it gives you a good example. Right at the top is the K20s. You can see that is 5.6 seconds, just kind of not at all useful. The Azure K80s, the K80s is still the workhorse of the data center. While we talk about exotic GPUs like Pascals and Teslas and stuff like this, the K80 is still the vast majority workhorse of the data center. And it is reasonably priced as well. So those are the numbers. If you can go to a 4K80 machine, you're down to about 1 second, which is getting there, but not quite good. Now here with the M40 and the Minskys, we are really getting into business. But I would like to point out, interestingly, again, a point in favor of Minskys, is that you get almost half in terms of the time, and the cost is not that much more. The cost numbers, different vendor, it depends on the source of where you're having. This one is from a cloud vendor called Cirascale, their website. And don't look at the absolute numbers because, that will depend. But the relative numbers are quite illustrative. Okay, and I think that is my last slide, yes. A little bit about us. We are an existing kind of deep learning vendor to IBM. We are vertical agnostic. We work with automotive, finance, and pharma. NLP, machine vision, control systems. NLP is the one I just talked about, but we, of course, do a lot of work with machine vision as well. Very large neural nets, not 16,000 layers, but we do work with VGG and ResNet, which is kind of the state-of-the-art large neural nets, and we scale them across multiple servers, etc. The other very interesting application, which maybe sometime in the future we can give a talk on, is using reinforcement learning for control systems. That's also something we specialize in. We are full stack experts, so we kind of understand hardware and all the way up to the kind of the mathematics of neural networks. And we help people, we help guide our customers all the way from what are the problems that are good for deep learning, to how do you create your data sets. We all know that that is the very important factor for success of deep neural nets, and all the way through designing, training the neural nets, deployment, and then final production. And the production step, very interesting and very important for deep neural nets, because at that point active learning can kick in. And as your users start using these systems, you can point out the ones where the neural network got the answers wrong, and you can save them all up, batch them up during inference time, stream it back into the cloud at night or when you have kind of downtime, and then accumulate all these error-prone examples and retrain the neural network. So it rapidly keeps getting better. So with conventional software, deployment is when you're done, and at that point you're just doing bug fixes. With deep neural network, the very cool part is that deployment is where it starts. And as more and more users start using these things, the performance keep getting better because you can keep retraining. Right, so that's the end of my talk. Thank you very much, the last talk of the day. And yeah, if you have any questions, I'm happy to answer them. Yes. It's a good question. I am not enough of an expert to kind of give you an in-depth answer on that, but I can hint, I can point to the general direction. Yeah, the Markov models are very good for kind of sequence and multi-step kind of stuff, which is indeed what is happening here. You use either RNNs or LSTMs or sliding convolutions to kind of tackle the sequential nature of this. Yeah, unfortunately, Markov models, you cannot backpropagate through them. So the credit assignment problem is not solvable in the HMMs. Yeah, I think that's my best answer. That see, I started off by saying you don't have to handcraft features because the process of backpropagation you can learn. You cannot backpropagate through a Markov model, and I think I know why, but we don't have to go there. I think that's sufficient. That the credit assignment problem is not easy to be solved on Markov models. But it's a good question, because it's very similar in structure to some of these LSTMs if you look at it, right? But the whole magic is about how do you assign those weights, right? Anyone here in the audience who's worked with NLP and deep learning? Okay, very much.